All right, welcome to section 1.3 part 1. Another tough section here. This is section is called continuity, end behavior, and limits. Okay, so we're going to talk about continuity and limits today. End behavior will be in the next part. The essential question is what types of graph specific characteristics are important for functions. Okay, so once again, from the graph, what kinds of information can we gather? All right, so this joke over here on the right will make more sense once you actually know what this word limit means. Okay, so what we're actually going to learn in this particular video is how do we use limits to determine the continuity of a function. Okay, and you have no idea what that is because you don't know what continuity means, you don't know what limits mean. So that's what we're going to learn today. So continuity of a function. The graph of a continuous function. Okay. So what does it mean for a graph to be continuous? It means that the graph has no breaks, holes, or gaps. Okay, I actually missed a comma here. There's no breaks, holes, or gaps. Okay, what that means is we should be able to trace without lifting our pencil. Okay, so let's look at graph number 1 here. All right, so if I start on the left, I can follow this graph and I can trace the whole thing and I never have to lift my pencil once. Okay, same thing with this one. I can trace this whole graph, try to get as straight as I can, don't have to lift my pencil. Okay, same thing. Oops. A little hard to do on this computer. Okay, so these are 4 examples of continuous graphs. I don't have to lift my pencil if I want to trace them. Okay, so pretty easy comment. Continuous graphs have no breaks, holes, or gaps. Okay. One condition for a function f of x to be continuous at some point is that the function must approach a unique function value as x values approach c from the left and the right. And you're probably thinking, oh my gosh, this makes absolutely no sense. So we're going to look at a picture in a minute to show this. The concept, so this is a very important word here. This word limit is very important in pre-calc and in calculus. The concept of approaching a value without necessarily ever reaching it is called a limit. Okay, so we have this chart here. So I'm going to try to explain this concept of a limit. All right, so we have this blue line here. Okay, our important value that we're trying to figure out here is this c. Okay, so this point right here. So we want to look from the left side of the graph going towards that point, and we want to look at the right side of that graph going towards that point. And if you approach this c value from the left and the right, and it's approaching the same number, okay, it has a limit, and that limit is L. Okay, so this graph, if I'm going to the left to this red circle and I'm going from the right, this graph approaches this open circle here. So it says that the limit as x approaches c, so as x, so coming from the left approaching c and from the right approaching c, is equal to L, the y value. Okay, and that really, it will make a lot more sense when we actually do some examples, but that's called a limit. Okay, for a function to be continuous, every spot has to have a limit. All right. So next part is what are discontinuous functions, and it probably makes sense. Discontinuous functions are functions that are not continuous. Okay. So that means that we can't trace it without lifting our pencil. Okay. So I'm gonna start here. Oh, come to a break. I have to lift my pencil to get over it. Okay. Come up here. Oh, I go to a break. Oh, I have to come up here to the top. Oh, another break down here. Okay, so I have to lift my pencil a lot of times to get to this graph. So this is a discontinuous function. Okay, same thing with the one on the right here. This function has 2 parts. One in the 3rd quadrant here, and then I would have to lift my pencil to get to the 1st quadrant over here. So both of these are examples of discontinuous functions. Okay, so continuous functions, no breaks, gaps, or holes. Discontinuous can have breaks, gaps, holes, all sorts of things, asymptotes, all kinds of things. Okay, so that's the difference. So, types of discontinuous functions. There are 3 types of functions that are discontinuous. Okay, So this first one here, okay, this one, number 1, is called an infinite discontinuity. So infinite discontinuity, which means at x equals c, if the function value increases or decreases indefinitely. So here's our c. Okay, so this is the point we're looking at. And if you notice the graph, it goes up infinitely to the right and infinitely to the up. And when we approach c from the left, it goes infinitely down. Okay, so when you have an increase or decrease indefinitely as x approaches c from the left and the right, it's called an infinite discontinuity. So that means it has an asymptote. Okay, what does it mean to have a jump discontinuity? So the second type is called a jump discontinuity. It has jump discontinuity at x equals c. So once again, here's c. If the limit of the function as x approaches c from the left and the right exist, but have two different values. So if we approach c, okay, c from the left, this part of the graph is approaching this spot down here, the negative number. If we approach it from the right, it approaches some totally different number. So they exist, but they're approaching two different numbers. Therefore, we have a jump in the graph. Okay, this one, and trust me, this is tough stuff. So we're going to talk about this more. The third type of discontinuity is removable discontinuity. Okay, a function has removable discontinuity if the function is continuous everywhere except for a hole at x equals c. So notice here's c, the graph has a hole, so it doesn't equal. So from the coming up the graph, oh, it's good everywhere. It jumps over that dot and then it continues on in the infinite direction. That would be called a removable discontinuity. All right. This little sentence down here is also important. Infinite and jump, okay, so the number 1 and 2, infinite and jump, are classified as non-removable discontinuities. So it's the opposite of this one. These are non-removable. Can't get rid of them. Okay, and with that will make more sense also when we do some more examples. All right, so how do we test to find out if something is continuous or discontinuous? Okay, there are three pieces here. 1, 2, and 1, 2, and 3. Okay, it has to work for all three of these. Okay, and I'm not going to go over explaining these quite yet, but we're going to do two examples and we're going to see how these work. They have to work for all of them to be continuous. All right, so here's example number 1. It says determine whether f of x equals 2x squared minus 3x minus 1 is continuous at the point x equals 2. Okay, justify using the continuity test. So what we're doing is we're using this test on the previous page to show that this function is continuous, that there's no gap, break, or hole at x equals 2. Okay, so part 1 of the test is, does f of 2 exist? So if I plug in 2, does it work? Okay, so does f of 2 work? So 2 times 2 squared minus 3 times 2 minus 1. So all I do is plug in 2 in for x. So this would be 4 times 2 minus 6 minus 1, 3 times 2. So 8 minus 6 minus 1 is equal to 8 minus 6 is 2, 2 minus 1 is 1. So f of 2 is equal to 1. So we're going to keep that in the back of our mind. So it passed part 1. F of 2 is equal to 1. It has an answer, so it does exist. All right, part 2, it says, does the limit at x going to 2 of f of x exist? So how would I find the limit? Okay, so we're going to use our calculator for this part. What I've done is I've graphed 2x squared minus 3x minus 1. Okay, there's my graph. Okay, so I can see here that at 2, my graph seems to work. Okay, it seems to have an answer here. So what we're going to do is we're going to use our table. All right, and I'm going to go to second window. Sorry, I need to put my cat out of the room. So you need to go second window, and this is our table setup. All right, so we are going to start at our table at the number that we're trying to find the limit of. So we're trying to find the limit at 2. So I'm going to start my table at 2. Okay, and then I always tend to go by this means change a table. So the table is going to go by 0.001 because we want to get really, really close. So our numbers are going to change by 0.001. All right. So we're going to go to second graph. And we're going to look at our table. All right. So here's 2. All right. So let's see here. So at 2, our function is equal to 1. At 2, our function is equal to 1. So I'm going to put that in my little table here. At 2, our function is equal to 1. All right. So I'm going to go and I'm going to see what happens if we go from the left towards 2. Okay. All right. So I'm going to go 3 out. So 1.997, 1.997. Our next number is 1.998, 1.998, and then 1.999. So remember, we're going by 0.001. Okay. And on the other side, what are our numbers? 2, 2.001, 2.001, 2.002, and 2.003. And we want to see what these values are equal to at those spots. Okay, so at 1.97, it's equal to 0.98502. So 0.985. Okay, what about 1.998? 0.990. Okay, 0.990. And then third one is 0.995. 0.995. And then let's look at 2.001. 2.001 is going to 1.005. 1.005. And then 1.01. 1. And then I need to go down one more number. 2.03. It's 1.015. 1.015. All right, so what we're going to do is we're going to look at this table, and this should help us tell us if the limit exists. Okay, so if I'm starting at the left and I'm going towards 2, these numbers 0.985, 0.990, 0.995, they're getting really, really close to the number 1. Okay, what about the numbers if I'm going to from the right? 1.015, 1.01, 1.005. Once again, these numbers are getting really close to 1. So what we can say is that the limit as x approaches 2, the graph, the function, is equal to 1. Okay? Because if you notice, from the left it's approaching 1 and from the right it's approaching 1. So the limit is equal to 1. Okay? So that does exist. The left and the right side, if they approach the same number, the limit exists. So check mark. We're good for that one. We are also good for the first one. F of 2 equals 1. That exists. Now for the last part of proving if this is discontinuous is to show that the limit of your function is equal to the same thing as part 1. So is number 2 and number 1 equal to the same thing? Okay. What was the limit of our function? That's part 2. It was equal to 1. So this part is equal to 1. And what was f of 2 equal to? F of 2 is equal to 1. So this is also equal to 1. So are they equal? Yes. Okay. So is this function continuous at x equals 2? Yes. It passed all 3 parts of that test. Okay. All right. So that's pretty tough stuff. So let's do one more and hopefully we can get it. And as you can see, this graph is, and this is the point we're looking at too. This graph is fully continuous at that x equals 2. There's no gap or break at x equals 2. So yes, it's continuous. All right, so let's do one more here. So we just have a new equation, and we want to know if it's continuous at x equals 1/2. So the first thing we need to do is, does f of 1/2 exist? So I'm going to plug it in. 1 over 2 times 1/2 plus 1. So I get 1 over, what's half of 2? Well, that's 1 plus 1, so my answer is 1/2. So f of 1/2 equals 1/2. So does f of 1/2 exist? Yes, it's equal to 1/2. So the first part works, yes. All right, now let's see if the limit exists. Okay, so what I've done is I can show you what I did here. I went back to my table. Actually, I need to go in my y equals. I'm going to turn this one off, and what you have to do is you have to graph 1 over 2x plus 1. I'm going to turn that one on. Okay, so here's my graph. So we can see that there's something happening here. And we're going to go to second window, we want to know if it works at what number. Okay, what number do we want to 1/2? So I'm going to make sure my table is starting at 0.5. And we're going to go by 0.001 again. So I'm going to go to my table. And you can see here that I have copied and pasted onto your notes this table that I just found. So let's look at the table now. All right, so here is the number that I want. 0.5 was equal to 0.5. That's what we proved up here. F of 1/2 is equal to 1/2. So coming from the left, 0.497 was equal to 0.5015, 0.501, 0.5005. So these numbers are getting really close. 0.5005 is really close to 1/2. Now coming from the other direction, 0.503 is 0.4985, 0.499, 0.4995, and you can see that those numbers are also getting really close to 1/2. So does the limit of f of x exist? Yes. It's equal to 1/2. So the limit as x approaches 1/2 is equal to actually 1/2. 0.5 is equal to 0.5. So it works. Okay. So as long as parts 1 and 2 are equal to the same thing, part 2 was equal to 1/2. Part 1, f of 1/2, was also equal to 1/2. You know that this graph is continuous at x equals 1/2. Yes. Okay, so let's look at the graph. So here is the graph. Now it looks like it's not continuous. Okay, it looks, but we're looking for 1/2 right here. What's my graph equal to at 1/2? So from the left-hand side, you can see that the graph is getting really close to that number. And coming from the right-hand side, you can see that it's continuous here. There's no gap here. There's a gap. It just doesn't happen at x equal to 1/2. So therefore, the graph is continuous at 1/2. X equals 1/2. Okay. I know this is confusing. We're going to make sure we talk about it, but I think with a little bit of thinking, I think you guys can get this pretty good. So I will see you tomorrow. We'll make sure we go over some examples.